Okay, it's a bit of a shame that you can't actually do this lab in the on-ground class because students tend to like this lab. They find it interesting. Informally, this lab is called the flame test lab. Usually, I think the more formal name is periodic properties, something like that, of atoms, something like that. Anyway, I am going to talk about a lot of things that don't seem related to atoms, and at least at the beginning. So here we go. First thing I want to talk about is light, and I'm going to try to run this the way that I run the explanation in the lab. I ask the students, what's that? Students say it's a rainbow. I say, what are the colors of the rainbow? Every once in a while, some of the students know the colors of the rainbow in the order that they come in, and they'll say something called Roy, G, Biv, and those, that's an R. The R in Roy, G, Biv stands for red. Basically, the colors of the rainbow are red, orange, yellow, green, blue, indigo, and violet. You don't need to know this, but basically that's where Roy G. Biv comes from. Those the first letter of each color name. And if you look at the colors of the rainbow, they always come in that order. In other words, red is on one side, and violet is on the other side, and green is in the middle, etc., etc. So some of the stuff that I'm going to tell you here is, I don't have time to go into why it's true. Some of the other stuff that I'm going to tell you is complete bullstein. It's a lie, but it's close enough to the truth that it'll let you understand, get a reasonable idea of what's going on. But I'm sort of letting you know that it's a bunch of baloney just because, if some legitimate scientist came along and listened to this, they'd probably have a heart attack. Okay, so here's the stuff that's true, that I don't have time to go into why it's true. Every different color of light has a different amount of energy. What I mean by that is if I have a certain amount of red light, it has a different amount of energy than that same amount of violet light, let's say. And there's a little bit more to this. Violet light has the highest energy. So light that's over here, highest energy of the light that we can see. So has more energy than blue. And as you travel in that direction, the light has less and less energy. So blue light has more energy than green because green is a little bit more to the left in my rainbow there. Green has more energy than red. And red colored light basically has the lowest amount of energy, pound for pound, of the different colors of light that we can see. If you've ever heard of ultraviolet light or UV light, people often tell you to avoid UV light. And the reason is ultraviolet light is over here. It has even more energy than regular old violet light, and it has so much energy that sometimes the energy from UV light can be absorbed by a lot of the molecules in our body, and it can damage those molecules. So that's basically why people are telling you to avoid UV light, because it has so much energy that it can damage a lot of the important molecules in our body. But the idea here, different colors of light, different amounts of energy. All right, here's a new topic. I'm going to talk about stairs. Imagine that I have a person standing on the ground floor there. There's my beautiful person. And I usually ask the students in the class, does it take a certain amount of energy for that person to climb up a step? And everybody says yes, because it does. You have to use some energy to climb up the step. And I say, well, if the person is up here, they fell back down to the original spot on the ground, they would release some energy. And that is correct. They would release a certain amount of energy. And then what I say is that if they fell down exactly the same way, and I know that's hard to do, but pretend that's possible. If they fell down exactly the same way over and over again, from the first step down back to the ground, they would release the same amount of energy. You kind of take my word for that. And I say, all right, here's a different set of stairs. Here's my same person. What's different about this new set of stairs? Hopefully it's pretty obvious, but the size of the steps are bigger. And so next question I would ask is, does it take more energy for this person to climb up the bigger step? And most people would probably say yes, and that's correct. So there's my person climbing up the first step. So if they fell back down that step to the ground, would they release more energy than when they fell down one step over here? And hopefully you'll agree that they would release more energy if they fell down the bigger step. If you want an extreme example of this, you could have a person on top of a building. So here's my building with some windows, and it's one big step to the bottom. And if they basically stepped off and went to the ground that way, they would release an awful lot of energy onto whatever is waiting for them at the bottom. So bigger step, bigger fall, more energy released. Same thing though, if they fall back down the exact same way every time, they will release the same amount of energy every single time. So, all right, so we're talking about different colors of light having different amounts of energy, and that is Binksy the dog. She apparently found a bad guy. Different colors of light releasing different amounts of energy, or having different amounts of energy, and climbing up and falling down steps requires energy, and you release energy. So what does this have to do with atoms? Well, the electrons in atoms can climb and fall too. And this part is the lie, although there's some truth here too. So this is some atom. Those are supposed to be my protons. I don't really care, right? This is completely ridiculous atom. It has a lot of electrons in different energy levels. That's energy level 1, then that's energy level 2, etc., etc. And the idea here is that you can make electrons climb and fall too. So here I have an electron on my stairs, and I think it corresponds to this electron over here. And if I give this electron some energy, I can make it climb up an energy level. Just like if I gave this electron some energy, I could make it climb up another step. And so I'm going to do that, and there's going to be an amazing animation. So check this out. Everybody see that? The electron climbed up an energy level, or climbed up a step. I'm going to show you again. There it is. It climbed up because I gave it some energy. When the electron climbs up to a different energy level that it's not normally at, you say that the electron is in an excited state. So there it is. It's very excited. And almost immediately the electron goes back down to its original spot, kind of falls back down. And if it falls back down, just like if you fell down a step, you would release some energy. Does that make sense? Hopefully it makes sense. And so, but what I'm going to tell you is the electron basically falls back down the same way every time, and it releases the same amount of energy every time. But when it falls back down, the way that it releases energy is it releases energy as light. It releases energy as light. And because it's releasing the same amount of energy every time, it releases a very specific color of light every time. So this electron, my excited electron, is going to fall, and check this out. Maybe it releases red colored light every time it does this. And another term to know is that when the electron returns to its original spot, you say that the electron is in its ground state. Hopefully that makes sense, because when I was drawing stick figures, I was saying the person started on the ground. So this can happen with electrons in atoms. Here's a different atom, or here, some big, ugly, ridiculous atom that doesn't really exist in the real world. The major thing that I want you to know that's different about this atom compared to the one on the previous slide is the size of the jump to go from the second to the third level is bigger than it was in the atom on the previous slide. You can see, well, I've got bigger stairs now. So it's going to take more energy to get my electron to jump from the second to the third level. But I can do it. And check this amazing animation out. There it is. It has jumped to the next level. And you all remember what state it's in. It's in the excited state. And almost immediately that electron is going to fall back to its original spot. And since it falls back more or less the same way every single time, it's going to release the same amount of energy every single time. And since it's releasing the same amount of energy every single time, it's going to release a specific color of light every single time. But it's releasing more energy this time, so it's going to release a different color of light. So maybe this time it releases violet colored light, something like that. So you can give electrons energy, make them jump up a level, or they can even jump up more than one level. Those electrons will fall back down, they'll release energy, and they'll release it in the form of light or other things that are related to light. And so what's the point of this? The point of this is that all of the atoms are slightly different in the way that the levels are separated from each other. You can think of it that way. And because of that, every different atom has its own fingerprint of light, of colors of light that it releases when the electrons basically jump around and fall back down to their original positions. So there are different sized steps between energy levels for the electrons, and what that means, I can't emphasize this enough, is every different kind of element emits its own unique fingerprint of colors when you give the electrons of one particular atom some energy. So here are some examples. Hydrogen is one kind of atom. If you excite the electron in hydrogen, hydrogen usually only has one, it can jump to many different levels and then they can fall back down to their original spots. And those electrons, that electron, depending on where it's falling from, will release this fingerprint of colors. There's this red color, there's this kind of blue-green color, blue, and kind of some purplish stuff. And those colors are a fingerprint for hydrogen. Only hydrogen does that. Sodium, if you excite some of the electrons in sodium, it releases these two slightly different colors of yellow light. Helium has its own fingerprint, neon, mercury, etc., etc. And this is true for all of the different kinds of atoms. So the thing about this is, if you excite the electrons in an atom and you look very carefully at the colors that are released, you can actually figure out what kind of atom you have. So who cares? Probably nobody cares. But this is how fireworks work. If you want blue-colored fireworks, you basically take an explosive and you add in a chemical that releases blue light when you excite the electrons. If you want red-colored fireworks, take the same explosive, you add in a chemical that releases red light when you want red fireworks. This is how certain areas of astronomy work. If you're a huge nerd like I am and you watch the shows on PBS where they talk about some star that's a zillion miles away, and they'll say, oh, that star is made of this element and that element. Nobody's ever been to the star. No one has ever been able to take a sample back. But in something related to what we've been talking about, if you look very carefully at the colors that are that you're sort of seeing from the star, and you can figure out what types of elements are there just based on the colors. So certain areas of astronomy rely on this idea. This is an old article from 2012. Back then we sent a robot to Mars called Curiosity. So we sent some robot to Mars. This is from the New York Times, and it says, on Sunday, the robot fired a laser instrument, hitting a rock with 30 bursts and analyzing the atomic makeup from the resulting flashes of light. So they're doing the same thing, right? They can tell at least a little bit what those rocks on Mars are made of just by looking very carefully at what colors of light are released when you excite the electrons. So, at some level, you don't even need to take the rocks back to at least figure out some things about the rock, just based on this idea that electrons release different colors of light depending on the atom that they are part of. So the lab that you would have done on ground, and there is no way that you are going to be able to do this at home because, well, it involves flame. So the way that you excite the electrons in your atom is you set the material on fire or you heat it up. It's a little bit dangerous. Even in lab on ground, I don't expect everyone to live. The ones who do, though, have a reasonably good time and they take pictures. But basically you take, well, I'll show you what you do. You get a Bunsen burner, so you get this flame, and you take different liquids that have different materials dissolved in them. This is calcium chloride, this is called potassium chloride, etc., etc., etc. And take this little device, which is called a loop, and you dip this end of the loop into the first liquid, and then the liquid ends up right there on the loop, and then you take that liquid and put it in the flame. And as this liquid kind of burns away and evaporates, the flame changes color. And I forget what calcium does. I think it's kind of yellowish, kind of yellowish orange, something like that. And so the flame changes to that color temporarily because the material, the electrons in the calcium are getting excited and they release that kind of color. And then the liquid burns away and it turns back to blue. Then you wash the loop, you dip it into the next liquid, you dip it into potassium chloride. The potassium chloride liquid is there. Put the loop in the flame, burns away, the electrons get excited, they fall back to the ground state, they release a different color. And then the students write down the different colors. They say, oh, calcium releases a certain color, potassium releases a different color, etc., etc. I remember barium. Barium releases puke yellow, something that's kind of yellowish green that looks like barf. Strontium is pretty, it's kind of bright red. Copper is pretty cool, that's green. Sodium you've seen in real life because you use table salt. At least if you have a gas stove, you may have seen it. So that's kind of yellowish orange, and pretty orange. Lithium is also kind of pretty. It's kind of a deep red. Anyway, so you'll burn these things, you'll get different colors. And then what you give the students is you give them 3 mystery liquids. And each of the mystery liquids is going to match one of the materials that they already tested, and they're supposed to figure out what the mystery liquids are made of just based on the colors. And then there's a little bit more to do in the lab itself. So here's the lab. You're supposed to watch the video. They'll probably give a very stuffy explanation of what I just did. And you can at least see these colors and these colored flames on YouTube. I'm sure that's where that video is pointing you to, some reasonably good video showing you the colors of the flame. Then you have these you have these unknowns, and you're going to try to figure out what they're made of based on the colors that they release. You're cooking pasta in water and you've salted it, and so you can answer this question. There's another question. More videos to watch. Some of this you can certainly do. I may remove some of these rows because they're a little bit overkill. Something related to valence electrons. Hopefully we've gotten to valence electrons by the time you do this. There's another video on atomic radius. If you don't know what a radius is basically if you have a circle or a sphere, the radius is the distance from the middle of the circle or the sphere to the edge. And they're talking about atomic radius. So what they want you to do is they want you to think of the atom as being like a ball, and you're measuring how big the atom is based on what its radius is. So if you have an atom with a big radius, it's going to be a bigger atom. If you have an atom with a small radius, it's going to be a smaller atom. Then there's this weird chart, which you're going to have to answer some questions about, maybe. Here they are, atomic radius versus atomic number. This is element symbol, but really it's atomic number on the x-axis. Then there are some questions, 8 and 9 here. Anything else? A bunch of other questions. Again, some of these I might remove because they may not be the best questions ever. But that is it. So have fun pretending that you're setting things on fire. Bye-bye.
You know the spirit of the party's